that correct?
Looks good.
Okay. A few minutes ago, David asked me a bit about solid rock lectures, and I made a few comments that I'll pass on to the rest of you. As the Lord drew me into this ministry to reach out to the church with the knowledge that he had provided for me in studying geology for about half a century, I decided it would be wise to try to have an organization that could accept, say, gifts to it as a nonprofit, so that we could offer to seminaries that we could come and give workshops at seminaries at no cost to the seminary. And that has worked out quite nicely for us. And in fact, Greg Davidson, my colleague with whom I'm really bonded together in this effort from geology and geochemistry, was able to apply for and got a very nice grant that we used. So for over a 3-year period, we had these funds with the stipulation that we would reach out to seminaries, which we did. So we got to 12 to 15 seminaries over that time period. So that's the context then when you see solid rock lectures with Earth as God's creation. So there's just a little bit about that. So our topic today gets to the context then of the clocks that tick for millions of years.
Hey, Ken.
Yes,
Ken,
please.
if you want to reach to Solid Rock Lecture, what is the website?
It's just by that name, Solid Rock Lectures.
Okay.
And when you do so, so it gives our mission and what we're about. Right now, we have it that there are 3 of us that are speakers under that name. So there are bios for each of us as speakers when we do get to go to a seminary. And then, but I'll give you a heads up that it is not active as many websites would be when a organization has a staff, a full-time staff. You know, then there are things added to it, et cetera. So once you've looked at ours, it does remain static for informational. So we don't have somebody that's continuing to add things to it. The things that we do write and get to try to get into publication mode, we tend to have in Reasons to Believe. I've done a couple of blog posts for RTB. And then Greg is a speaker for BioLogos. So he's put a couple of articles up there in BioLogos. So we seek to get them out on websites that are being actively updated by organizations that are have employees and continue to do that. So thank you for asking that question.
Thank you.
Yep. Okay. Well, in May, you saw this diagram. I'm going to change my view here a little bit. There we go. You saw this, that I always feel when I'm sharing things that I'm sharing creation story with what I've learned, that the earth is ancient and we have a magnificent creator. I showed this volcano last time also because it's a good reminder that Psalm 104 reminds us that he is active in his creation, touches the mountains and they smoke. And we read about the storehouse for snow and ice in the heavens, or the way God handles that. And he invites us to examine what we find out. Speak to the earth and it will teach you, and let the fish of the sea inform you. So he is inviting us to study and learn how he has done this over the millions and billions of years, as we learn and we'll learn more about and talk about this evening. So I'll gear toward 3 general topics that developed with my conversation with David. These nature's clocks do in fact tick for millions of years, and in fact also for billions of years, if you will. So I'll put in the context just sort of a few key pointers and topical areas. So we'll spend some time with plate tectonics as a backup support for radiometric dating. We'll spend some time on the Grand Canyon, give you an overview of the Grand Canyon book that we wrote in response to flood geology concepts that are spread in the church. And then David asked me to make some comments about the Persian Gulf and the nature of the way water came into the Persian Gulf some 15,000 years ago, as it might be related to Noah's flood. So those are the topical things that I'll go through. So we'll get started here with plate tectonics and how it helps to confirm the radiometric dating methods. The Earth's crust is made up of about a dozen plates that we call tectonic plates. And in the locations here where the arrows are separated, pointing away from each other, there is new crust being formed because of convection in the mantle, which I'll show in a diagram in the next slide. And where the arrows are pointing toward each other, we have the plates crashing together. And one incredible place of that is the Nazca plate crashing into South America. And it's the thing that triggers the volcanic peaks that are up and down along the Andes Mountains and the series of earthquakes that occur along that western side of South America. The one we'll talk about distinctly also is India crashing into Asia, forming the Himalaya Mountains. So that's another location where the tectonic plates are active. And you all remember the tsunami that hit Japan about, almost 10 years ago now, because this Pacific plate is moving to the northwest. Well, you might ask, what in the world drives this idea of the plates moving? 75 years ago, geologists thought that plates moving and separating in South America, separating from Africa was just absolutely impossible. And then as geoscientists continue to gather information of some of the things that I'll show you today, they recognize that in fact, the interior of the Earth with the core that is molten and hot, the outer core provides enough heat here at the boundary between the outer core and up into the mantle rock, that it heats the rock. And even though it's rock, it does move very, very slowly at snail's pace, if you will, deliberately very slowly, but it does move and it causes mantle rock to rise up. And as it rises up, then it eventually separates and gets carried outward and away from the mid-Atlantic ridge. And these are referred to as basically convection cells. Completely analogous, if you will, over here to the beaker in the laboratory, that with a Bunsen burner heating the water, it will rise as it gets warmer, and then it spreads out at the top and it sinks on the outside of the beaker. And that circulation continues as long as it's being heated. That same kind of process has occurred in these convection cells in the mantle as the outer core continues to heat that mantle rock and cause it to convect.
I have a quick question.
Yes, please.
Yes, the Bunsen burner, it's like a point. At one point it's heating, but the outer core, it's the whole thing that's heating everywhere at once.
Yeah. What happens is that in locations underneath a very large continent, let me back up here. For instance, now 180 million years ago, all these continents were together in a unit called Pangaea. So where that heat comes up under a large continent, that process begins to heat it up and then it begins to break apart. We currently have that type of thing happening right here in East Africa connected to the Arabian plate, because that plate was big enough. Heating of the mantle rock caused that to break apart, so that in the Red Sea today, the Red Sea is a very young ocean basin, if you will, whatever it is, say 100 miles across or something like that. It has a rift down the middle, and the Arabian plate is moving away from the African plate. So that's a similar context now. Does that help?
I guess he's asking, are there like hotter spots in the core?
Oh, the distribution of the heat in the core.
Right.
I've not reviewed that. I do not know. Yeah. The point of the core heating up under a very large continental area is that the continents are incredibly thick, whereas out in the ocean basins, the plates are thinner, so heat can be distributed and get up through it more readily. So the continents break up because heat isn't being as readily dissipated, is about the level that I understand it.
Okay. And so basically anywhere the lines are, you get earthquakes.
Everywhere these blue lines are will be earthquakes. That's correct.
Okay.
Yeah. Now notice, let's look here at the Mid-Atlantic Ridge. Okay, notice here. Because those arrows are going apart, there are earthquakes, but they're only on a narrow band because the plates are moving apart. In contrast, in South America, as the Nazca plate is moving east and diving in under South America, the band of earthquakes is like 100 or 150 miles wide. So it's very, very wide. And when with India crashing into Asia, the band of earthquakes is all the way from Nepal and up into the whole China, the highland areas of southwestern China. So the distribution of earthquakes is controlled by the plates moving. At separation points, the band of earthquakes is narrow, and at crashing together points, the band of earthquakes is very wide. Okay, another question on that?
I didn't hear all of it. Was it the band of earthquakes is very wide at the point, where is it narrow again?
It's narrow up and down the Mid-Atlantic Ridge.
Oh, okay.
Okay.
I just remembered.
Spreading. And it'll be narrow here in the Eastern India, because that's separating.
I just remembered that I read something about mantle convection a long time ago by Dr. John Baumgartner.
Yeah.
And so I just remembered, yeah, it does have a lot of convection, and he made some sort of a Fortran program that was on supercomputers that calculate this kind of stuff.
Yeah. Yes, he did do that. He's a genius and an expert at doing coding to run models. Yeah. Okay.
Ken,
let me go on here.
Ken,
Yeah, go ahead.
I was curious about, is there there should be a boundary between on the west side and the east side between the North American plate and the Eurasian plate, but you don't show it. So can you mention that or?
Okay, the North American plate, okay, over here on the Pacific side, the North American plate includes the North American continent plus the oceanic crust that goes out to the east to the Mid-Atlantic Ridge. That's a single plate. The eastern United States is what's called a passive boundary. It does not have tectonic activity in separating. Now, is that answering where you made your?
No, no, what I was really asking about is
Where?
on the eastern side of the Eurasian plate and
Over
the
here.
western side of the North American plate basically in the Arctic region.
Oh, up
You
in the
don't
Arctic.
show any boundary. What's the boundary between them?
Okay, the Eurasian plate, in this case, in the Pacific, this Pacific plate is moving about like that, and it is diving in under the Aleutian Islands, forming all those islands. Here, over here on the eastern side of this map, the Pacific plate is moving to the northwest, and the chain, this causes the volcanoes on Japan. That volcano that I showed earlier in my slide is right up here in Kamchatka. Okay.
I think what Kirby's saying, if you look at the North American plate from Alaska,
Yes.
and then you keep going to the left, it looks like it connects to the Eurasian plate.
Okay. It does. I'm not sure what kind of boundary is in that area. With this kind of map where we've taken the globe and we've spread it out flat, we lose perspective up there at that very high latitude in the north and the high latitude in the south.
Okay, thank you. That's good.
Yeah, yeah. The reason I like the nature of well, toward the end, I need to show you an animation of the plates moving to help give you a perspective. But let's get through our topics and then look at that toward the end. Now let's look at the Hawaiian Islands. So where you were really asking about is what's up in here, because this is North America is one plate and the Eurasia is another plate, and this is stable. This is reasonably stable. So I guess maybe in relationship to each other, they're not really moving too much, but the Pacific, this whole Pacific plate is moving about in that orientation, which we're going to be seeing here as we talk about the Hawaiian Islands and the Emperor Seamounts. So we'll be looking at all of these, the big island of Hawaii to the south, and then the Hawaiian Islands here a short distance, and Midway Islands up in here somewhere. And then beyond that, there are even seamounts that are mountains that were formed down over the hot spot where the big island of Hawaii is now located, and they have been carried north and northwest. So one example is the oceanic crust that is moving to the northwest built up stress against the islands of Japan, and that stress built up to such an enormous degree that in that Japanese earthquake, there was the earthquake, there are volcanic eruptions, we had that devastating tsunami. And this plate movement is what causes mountains to form and moves the crust around. And you remember the nature of the devastating tsunami that hit that coast of Japan and impacted the nuclear power plant so drastically. Today in the Hawaiian Islands, this Kilauea volcano that's at the southeast end of that big island has been spewing out lava for decades and it's one of the most active volcanoes in the world with respect to the volume of lava that comes out. And it basically keeps on building that big island of Hawaii somewhat bigger and bigger at, certain number of extra acres per year, or however it plays out as it slowly grows. We had that experience several years ago and seeing the sort of a sequence of the lava flow that got into the news because the volume had increased enough and come down through terrain where people were living, crossing roads, causing damage, emptying up into the sea eventually. And our understanding geologically is that there is a hot spot down in the mantle that has been there for tens of millions of years. And it continues to spew lava up through a plume, and that comes out on the islands. And it's been coming out of Kilauea for probably a couple 100,000 years. And in fact, there's a new island, or excuse me, there is volcanic lava that is basically building up to the south of the big island, which will eventually be a island in the future when enough lava has built up to come up to the land surface. As the plate moves to the northwest, it carries the islands along, and gradually the thickness of that plate as it cools down subsides. And so there are a series of islands, and then further to the northwest up toward the Aleutian Islands, we have seamounts that are submarine mountains that were formed over this plume, but have been carried to the north and northwest. In terms of ages, of course, down here at Kilauea in the southeast corner, those would be zero ages because that's flowing today. On the big island, there are some ages of the rocks that are 400,000 years. Then the next island up is 1.3 million years, then 1.9. And then Oahu with Honolulu has ages of 2.6 million years. And then the Honeymoon Island to the northwest of that is about 5 million years. So that's the range of time window when these Hawaiian Islands were formed. Now, the ages there that were listed on the Hawaiian Islands and now on all the rest of the islands, those are numbers that are derived in millions of years from the potassium argon radiometric dating method, which we'll get into radiometric dating then of these long half-life isotopes as I step through this yet in this talk. So notice here that we have a series of volcanic rocks that spewed out at very uniformly increasing ages from today down on the big island of Hawaii, up here at the bend when something happened that changed the movement of the tectonic plate at about 43 million years ago. And then ultimately the oldest age that geologists have discovered of those submarine seamounts is 80 million years. So here we see the evidence of the tectonic plate moving over a time period of 80 million years, producing islands as the sequence went by, because that plume in the mantle continues to send lava up through the plume into and through the Pacific Ocean crust. Well, we have a distance and we have ages derived from radiometric dating. And so we can calculate the rate at which that plate has been moving, and that is 3.2 inches per year. Having another sequence there from the bend on up to the Aleutian Islands is 1,500 miles, and that averages out to 2.6 inches per year. So as I step through this, this is basically using the potassium argon radiometric dating method to get the ages, and then because the plate is moving as a massive amount of rock to the northwest, that helps us to confirm that yes, those numbers made sense. If radiometric dating was completely off most of the time, we would not get a uniform increase in age. So a question that I'm often asked or that young Earth creation would ask, how can I trust radiometric dating? Well, here's what we're doing is we are comparing the potassium argon age with another data recorder that's suggestive of a long passage of time, and that is the massive Pacific Ocean plate moving. So there two are being tied together and we can get a rate of movement. Now, we have those 2.6 to 3.6 inches per year from a calculation of the potassium argon radiometric dating method and the distance. We can physically measure the rate at which the plate is moving today with satellite technology. So on many different locations on the surface of the Earth, geoscientists have done this. And so for that plate motion that was measured at Hilo, Hawaii, the rate of movement is determined today over the last 10 years, okay, with satellites to be 3.1 inches per year. So it fits very nicely with the estimates that were, or the calculations that were made with potassium argon between 2.6 and 3.6 inches per year. So here we're blessed with the opportunity of doing a current measurement actively today and giving us a chance to help to confirm that the rate today is consistent with what we have determined with the historical efforts of seeing that evidence of the increasing potassium argon ages from the Big Island on up to the Aleutian Islands. So do you have a question about that step?
I would ask, can satellites measure that accurately, I guess?
Yes, they can. Yeah, they can do them. And it's not just instantaneous because we've had this satellite technology for minimum of 10 years and probably longer in the military. When the same thing is done in the Atlantic Ocean basin, we can currently measure the rate at which North America is still separating from Africa, and that works out to about 1 inch per year.
Ken, it seems like there needs to be a point of reference for the satellite. That is a point on the Earth that's not moving, but there isn't any such point, is there?
Yes. The physics of the way they set up the grid to determine the nature of the motion, I've not dug into that enough to really give a cogent answer. So I'm not too sure. They obviously have to do those relative to each other, but I don't know how they establish the stable grid from which they determine the motion. So, but yes, that's a logical question and could prompt me to do some little digging, like how do they establish that frame of reference?
Yeah, that's interesting because GPS has like ground stations, but I never thought about the slow drift of the continents and stuff.
Yeah. Yeah.
Hey, Ken?
I do know that GPS, in terms of between the satellites and the GPS positions, they have to take relativity into account. I do know that that's part of the equations. But in terms of the grid, I have not investigated that enough to comment. Go ahead, somebody.
I was going to say, this is Paul Smith, that
Yeah.
they might be using star positions, fixed stars as their reference.
Could
If you
be,
can-
yeah.
And that wouldn't be dependent on what's going on the Earth at all.
Yeah.
And then couldn't you also use the poles? Maybe, I don't know. Because at the pole, there would be no other than just spinning if you were sitting on the pole.
Okay, well, let me go ahead and then press on and sort of give more details about the nature of these clocks that I've just mentioned, sharing with you one example there of potassium argon results. All radioactive atoms, because of the physics of the nucleus, undergo radioactive decay that obeys an exponential decay equation. So in this diagram, this blue patch, or this square, has 100 blue dots to represent 100 radioactive atoms. After the passage of one half-life, whereas the vertical axis is the percent remaining of an original number of atoms. So after one half-life, 100 of those radioactive atoms will have decayed to the daughter product. And so there are 50 blue radioactive atoms left here and 50 of the daughter product. Through a second cycle to the half-life, this will be 25 blue atoms left, down to 1/8, 12 if you will, 1/16, 1/32, 1/64, 1/28, etc. Notice by the time we get to about 7 half-lives, an original amount of 100% has fallen off to less than 1%. So in terms of measuring, and the 2 months ago, I talked about radiocarbon. Radiocarbon has an inherent limit down there about 45 to 50,000 years, because radiocarbon is getting out there at about 40, 45, 50,000 years.
And
And there's only about 1% left.
Is there anything which affects the rate of decay, temperature, or pressure, or anything?
Very good questions. And nuclear physicists have been testing this question every decade since radioactivity was discovered. So they have found that temperature, pressure, magnetic field, even a level of hitting it with a bomb conditions, not just pressure, static pressure, but even intense pressure, doesn't seem to make anything more than just a very small fraction of a change. The one type of radioactive decay that had the most effective change was that there are a few atoms that the radioactive decay happens because the electrons in the electron shell are squeezed in, and so basically electron gets into the nucleus from the shells on the outside. They've observed that that has a very minor impact, about the most, but most of these is less than 1%. And that's been tested over and over and over again. And in general, even those individuals that claim they believe the Earth is young, generally are willing to accept that the radio half-lives have been at least stable, but they're so desperate to find something to make the Earth go young. Even in spite of that, they say, well, radioactive half-life must have been changed in the past, but there's no way to produce the magnitude of that. No physical method issues in terms of the environment that we know about can change it beyond just a very small amount. Now, for igneous rocks, what's happening is that the parent atoms of radioactive decay and the daughter atoms are all floating around together. So it is very significant that we can do radiometric dating on igneous rocks. And what we're detecting is the time since the igneous rock cooled to a crystalline solid that traps and locks the radioactive isotope atoms into a crystal. And this is referred to as setting the timer to 0, T = 0. So that's the significance. And that can happen with volcanic rocks that come out on the land surface. It can happen with rocks that are below the surface and cool down. All right. But this step of cooling of a lava to crystals is significant to set the timer to 0. Now, I refer to calling them clocks in the rocks, but it's not really a clock. It's a timer, if you will. It's setting a timer and then it goes forward like a stopwatch. But clocks have a sort of a little more catchy term to describe the idea, but they're really timers, like a stopwatch. You set it, get it going, and then watch and measure it, look at it later to see how long it's been running. Here's one example then. Uranium-238 atom is a radioactive atom. It throws off 8 alpha particles, which are basically helium nuclei. And it ends up as the final stable daughter product is lead-206. And this is one of the very common radiometric dating methods referred to as uranium lead. My diagram is intended that, say, here some uranium was trapped in that black mineral. When it gets trapped in that crystal, it undergoes those decays, and the lead atom will still be there, can still be there later to be measured by in the laboratory. Or here I show an example in that tan mineral, another example in the tan mineral, another example there in the black mineral. I'll develop this a little bit more and talk a little bit more about this step of fitting into the lattice. In the case of uranium-238, the half-life is 4.6 billion years, which is in fact right about the age of the Earth. Now I have this as a schematic just to give you the concept. Say 400 million years ago, as a schematic, uranium-238 atoms are taken up into the mineral called zircon. It has its half-life of 4.5 billion years, and it undergoes decay to the lead-206, as I showed you in the last diagram. On the right-hand side, potassium argon, the potassium, the isotope of potassium that is radioactive. Now we know about potassium because we hear about it in medicines, and it's a very common element that makes up lots of rocks. But the potassium-40 is just a tiny, tiny fraction of all the potassium. Most of the potassium is potassium 38 or 39. I forget which it is right now. Okay. So potassium, again, when a big body of liquid rock cools down, potassium tends to go into a group of minerals that are called feldspars, which are silicon and aluminum and oxygen and some other elements. So in my schematic now, I have potassium-40 atoms here in the feldspar, and it has a half-life of 1.25 billion years. So notice the half-lives are different. So the potassium-40 will disappear more quickly than the uranium because the uranium has a longer half-life. Now, if I go pick those rocks up today, here on the left side in the zircon, now I have many of the uranium-238 atoms have been changed by decay to stable atoms of lead-206. and it goes at the slow rate because the half-life is long. Over here in the feldspar, the potassium atoms have mostly decayed away in my schematic, and there are only 2 potassium-40 atoms left. So we can take these zircon or feldspar into the laboratory and measure the proportion of potassium and the argon, or the uranium and the lead, and make a calculation how long ago that timer was set to 0 for these minerals.
One question. So
Yeah.
when you showed the zircon, like if you go back 2 slides, so everything was uranium on the left and everything was potassium on the right.
I'm just using this as schematic,
Okay. Okay.
only schematic, just to help to visualize.
Okay.
Yeah. Uranium would not be in all those.
Right.
It is not in all the zircons, and it's not all potassium 40. It's all the other thing.
Yeah.
So
You're setting the time to 0 at this point. It's 0 start.
when it cools down and the crystal forms, that's the setting a timer to 0. Yeah.
Yeah. I guess it's complicated because at time 0, there's already some uranium and some lead in the sample.
The unique thing about zircons is when zircon forms, it doesn't take up lead.
Oh, got it.
Okay.
Okay.
Now that has to be tested, you know. If the zircons are found to have some lead, then it has to be corrected for.
Okay. Yeah, that was like the missing piece of, how do you know what 0 times 0 is? Okay.
That's true.
Good.
And likewise, the feldspar, if it is incorporated when it formed some argon 40, that has to be detected and analyzed, and there are ways to do that. Because what we're measuring when we measure the argon 40, we only want to measure the radiogenic argon 40 that has come from potassium 40 in the crystals. And we'll see some of that as we step through some more here. Okay, let me use, again, kind of schematics to help get the concepts across. So here I have a zircon crystal, and I have 4 uranium-238 atoms in it. There I have another schematic of a zircon crystal, and of the 4, 2 of them have turned to lead-206. So that represents from 4 to 2 is 1/2. So that represents 1 half-life in my schematic of the idea. And as I said, that half-life is 4.5 billion years. Now let's look at the crystal structure a little bit more. Zircon is made up of zirconium elements, atoms of zirconium, atoms of silicon, and atoms of oxygen. The uranium has the potential to substitute in this crystal lattice for the zirconium. So sometimes uranium-238 atoms get into that crystal lattice here. All right. Now it's kind of trapped in that crystal lattice. I nickname them bird's cage, if you will, because uranium substitute for some of the lattice sites in the crystal for zirconium, and then it undergoes the radioactive decay process and ends up as lead-206 staying in that cage. Then I can comment now that we also need methodologies to develop an understanding if some of those lead-206 atoms have leaked out of that cage. We have to find a way to detect that and take that into account. The dominant radiometric timers with long half-lives I've just been mentioning uranium-238. I've mentioned potassium-40. Rubidium-87 is pretty common. Rhenium-187 is another. Uranium has a second half-life. Excuse me, uranium has a second isotope, 235, and each of these has a different half-life, and you can see how they're dramatically different. In a few moments, I'm going to be showing some examples of different rocks that have been measured with several of these different pairs of parent-daughter radioactive decay that end up giving the same result. And you'll recall that our carbon-14, we spent some time with 2 months ago when I was talking about radiocarbon and biblical archaeology. Now, to have confidence, if I get one piece of rock and I do a radiometric dating age by different methods with atoms that have different half-lives, and the answers come out the same, that is great supporting evidence that these methods, when they're applied correctly, that they can work well and they can work very well. So here's an example of nicely concordant ages of a igneous and metamorphic rock in Western Greenland. And there's the uranium lead. This lead is going to be a combination of the uranium-238 and 235. There's the rubidium strontium that I mentioned in the last slide. These are two others that I didn't have on the table, lutetium and samarium neodymium. But notice these, they all come in between 3.55 and 3.64 billion years. And the error bars are down here in the last digit, the third digit, or there's one that's 0.1. So plus or minus 0.1 at that. So this is nicely within about 1%. Very supportive evidence that these methods work. Same thing was applied to meteorites, a group of meteorites. Uranium lead 4.55, rubidium strontium 4.5, potassium argon 4.54, uranium osmium 4.62. In this case, I don't have the error bars on them. Okay, again, different kinds of rocks, concordant ages giving the same result. Now, you've heard that it was an asteroid that had an impact on the dinosaurs, and they had it great for millions of years, and then 65 million years ago, there was a devastating impact of an asteroid that hit the Yucatan Peninsula. And I chose not to do a group of slides of the significance of it. I decided just to go to the data, and I'll give you an idea of where these samples came from. So the asteroid hit the Yucatan Peninsula. It was so energetic, it melted a lot of the rock and it threw ash up into the atmosphere. So that from these samples of the asteroid impact, we find evidence of an ash layer in Italy, in Northern Europe, and in Colorado area, and up here in Saskatchewan, and in Montana. And there's so much, there was quite a lot of the rock from the impact that was turned to liquid, that as those pieces of liquid into little glass spheres, as those glass spheres were scattered among places and then collected from Haiti, from Mexico, from Montana, from Saskatchewan, they took the different radiometric dating methods in 5 different laboratories. And I can send you a paper that you can read all this data over here on the left. But the punchline is there are 187 samples that are in that list. I counted them all up. And all of these ages, measured by 4 methods, 5 different laboratories, are between 63.7 million years and 66 million years.
So when the
That's
asteroid,
crazy. That is crazy. I mean, if these radiometric dating methods didn't work, you'd never get these scattered all over like that and get coherent results. Yes, your question, please.
yeah. So when the asteroid struck, did it restart the clock to 0? That's the part
Yes.
that confuses me.
Yes, because when it struck, there was so much energy. There was lots of rock that was turned to liquid.
Okay.
Yep.
Can I-
It had to go to liquid or we wouldn't get these ages.
Ken, I got a question about, earlier you said that heat and pressure and a lot of these outside influences don't have any effect on the decay rate. But yet, when they're put into these samples are put into a molten state, that does reset the clock. So there's some kind of a threshold they have to pass before the clock gets reset, so to speak.
That is correct. Yeah, that rock that was down on the Yucatan Peninsula, those were old rocks. Okay. But in the process, the asteroid made them molten. And so the clocks were reset, T equals 0, by that melting step.
And so that's the same process that's happening in the core of the Earth. All that material down there is in a molten state, and the clocks won't set on those, so to speak, until they somehow solidify.
Solidify, exactly. Yeah, that's correct.
This is amazingly consistent. And this is a lot of work, all these hundreds of samples and.
Yeah. And to think that this has been done by the geoscience community, geochemists. So they have literally hundreds of thousands of radiometric dating method, of radioactive dating ages of all different kinds of rocks. And it doesn't always work. I'll show you one that didn't work quite as smoothly as this. But I want you to see some that do work well, because there are locations where ages are discordant because of the temperature of setting it. And I will show you one of those from the Grand Canyon as we talk here yet this evening in a little bit.
One thing that I'd like to clarify, the separating or the turning the clock to 0 really means that the material that was liquid cools, and so the uranium solidifies together. All the uranium solidifies and separates from the lead, which cools, which melts at a different temperature. So it's really the separation of different elements into globs of pure element of rubidium or whatever it is.
Right. Yeah. Well, and let's use the issue here of potassium argon. Okay. As you'd be aware, argon is a noble gas. It doesn't combine chemically with anything. So if a lava that has potassium in it cools slowly, at least slowly enough to let the argon 40 escape that might have been trapped there from previously, we can get a timer set to 0.
Okay, yeah, that explains a lot, that the materials are like separated and reordered.
Yes.
And then you need certain structure for the crystals. Okay.
Exactly. Yeah.
That makes good sense.
Yeah. Well, there's the geologic time scale. And all of these numbers, 100% of these numbers that are applied to the geologic time scale are all derived from radiometric dating of igneous rocks. And the geoscience community reviews these different boundaries over and over again. So for instance, this one of the Paleogene from the Cretaceous, up until about 5 years ago, we had that at 65 million years. And the issue is each of those boundaries is defined someplace on the Earth's surface. Most of these boundaries are going to be over in Europe. And the geologists get together and they make a decision, where are we going to pick this boundary? You know, what different parameters? So sometimes these ages are adjusted a little bit, but that's as well as the nomenclature is gradually modified somewhat. So I'm showing you the current version of the geologic timescale. Now, several geochemists came up with an ingenious method to estimate the age of the Earth. This is Meteor Crater out in Arizona. And the meteor that hit is a rock that has uranium in it, but it has no lead. Excuse me, I'm sorry. I turned those absolutely around. It has lead, it has lead isotopes, but it doesn't have uranium. Erase that one sentence I said that was wrong. sorry, I said it incorrectly. So Claire Patterson and the next person I'll show is George Tilton here in just a second. The idea is they got a piece of this Holsinger meteorite, and because it has lead only and no uranium, they can measure the isotopes of lead, which include the significant ones I'll mention right now are lead. I've mentioned lead 206 comes from uranium 238. Lead 207 comes from uranium 235. But lead 204 is not the daughter product of any radioactive atom. So meteorites are considered to be pieces of rock from our solar system that were formed at about the same time as the solar system, and then they come crashing to the Earth. So Claire Patterson and colleagues carefully measured the ratio of lead 206 to 204 in the meteorite, because they knew that in the meteorite, lead 204 would not be changed since that rock formed. But lead 206, okay, in this meteorite, yeah, and lead 206 is a value that's not influenced by uranium in this rock because it has no uranium. So lead 206 to 204 is what the Earth materials would have had at the time it formed. Now, the other person involved, and there's a third person, but this gentleman is special to me for the particular reason that I had my very first geochemistry class with George Tilton at University of California, Santa Barbara. And so my first geochemistry class, then I was prone to learn more about him after I had left, when I found out that he was a co-author of this paper, that original paper that gave us the age of the Earth. And he was indeed a very gentle and modest person, you know, in all of my dealings with him in that one semester that I had him. And he's described publicly as a man of integrity and et cetera. And I actually did speak to his daughter at one point, because I was really curious if with these good qualities he might be a Christian. And she reported to me that he was very active in his Episcopal church where they worshiped. I can't make a claim that he would have a strong evangelical perspective like we would, but he was certainly a man of integrity, and I can affirm that. Okay. So in the Earth, the uranium-238 will steadily decrease because of radioactive decay, and the lead increased because of the radioactive decay of uranium. So the equation that Claire Patterson and George Tilton wrote was answering this question: how long would it take the radioactive decay of uranium to change the lead isotope composition in those meteorites to the composition they find in the Earth's crust today? So conceptually, they're keying in on lead 206 to 204 in the meteorites, but the lead 206, 204 today in the Earth's crust will be larger because 206 has been increasing over the history of the Earth. And solving those equations, they ended up with an answer of 4.56 billion years. This was published in 1955 and 56, and that number has hardly changed since that time. So when I'm communicating and working with on Facebook or in a church or giving a talk, I really can say with a degree of confidence that we physically have evidence that the Earth is 4.56 billion years old, and this is the nature of the evidence.
You made the statement about the fact
Yes.
that uranium is increasing. Is that because of meteors and asteroids hitting the Earth?
No, uranium is decreasing. Lead is increasing.
Okay.
Due to the decay. And here's a completely random question. Have we found a meteorite that's older than this, that's maybe came from outside the solar system?
I haven't, let's see, I haven't reviewed that question, but something sticks in my mind that there have been a few rocks, yes, that are older than the 4.56.
Mm-hmm.
Now, a few isolated ones wouldn't be of concern to me because, you know, that particular piece might have a more complex history for some reason. So I seem to think there have been a few things found that do have some older ages, but I can't, I couldn't go to the papers right now. And I also would not recall how geochemists made an interpretation of that piece of evidence. Or maybe they couldn't, maybe they never could sort of sort out what might have happened.
I guess all that comets and asteroids are still created by the sun. Yeah. It'd be hard to get something from another star.
They're still within everything I know, they're still within our solar system. Now, what comes from outside our solar system? Galactic winds. Let's see. I don't know. I haven't reviewed that recently.
Yeah, hard to imagine.
I'm groping there. I'll be just candid. I have enough challenges trying to communicate with truth and love to people who think the Earth is 6,000 years old. And that
I just looked up the older than the Earth.
Yeah.
And they're saying that a protoplanet in the early solar system spawned a unique type of meteorite. And there's one that hit in the Sahara Desert in 2020.
What kind of age?
And the age is 4.6.
Oh, but I treat that as insignificant.
Yeah.
Does either one say like 5 billion or 6 billion or 7 billion?
No, that's all. I'm just reading the initial.
Yeah.
So I'm reading about the lunar samples. They're all within this range too.
Yes. The lunar samples are 4.5 or somewhat less.
Yeah.
And I believe everything on Mars also. Well, let's see. Do we have isotopics on Mars? I think there may be some rocks that they believe did come from Mars, but I forget the key components that distinguish that. Okay. That's what I have to share about radiometric dating with long half-life isotopes. In the abstract, I thought, let me show you one thing that's not quantitative, but it's clearly evidence that the Earth is old, beyond 6,000 years. These are the chalk cliffs of Dover, about 400 meters high. And those chalk cliffs that show up on the UK side of the English Channel also are exposed over on the French side also. All right. These chalk cliffs are made up of calcium carbonate or calcite. There's a family of marine algae called Cocolithophores, and the cell of that single-celled organism lived inside this little shell, if you will, or these little platelets. Each of these little platelets we refer to as coccoliths. The cell lives in there, manufactures these calcium carbonate shells to protect them. And when the cell dies, they break apart and fall to the bottom. And there's sort of one style over here on the left, and this one is sort of similar but somewhat different. The shape of the characteristics of the little coccoliths is a little bit different. But once they fall to the bottom, they build up with a jumbled pile. These are about just a few microns across, all right? From the diameter of those, just a couple of microns, all right? These chalk cliffs are up to 400 meters high. In modern locations today in the oceans where these coccoliths accumulate, and it's able to measure that accumulation, it's in the range of 0.01 to 0.1 millimeters per year in terms of the rate at which the Cocolithophores, single-celled organisms, can take calcium carbonate out, build their shells, the cells die, and the plankton die, and then the platelets begin to fall to the bottom. Radiometric dating methods there at the chalk cliffs give a context that it seems they were basically formed over a period of about 30 million years, okay? Now, there wouldn't be dates directly on these coccoliths because there isn't uranium or rubidium in there to do that. So those radiometric ages are other related igneous rocks that are in the general depositional area region there in the, well, let me go in the diagram. For instance, maybe one of these layers down here has some igneous rocks in it. So they get an age of some of those. 400 meters of chalk over a 4 to 30 million year time period represents just over the 0.01 millimeters per year. So it's within this range of what marine biologists have observed today. And I did end up pulling an article that I had somewhere on my files that came from Answers in Genesis. And here was roughly what the conclusion was. They said that these were formed basically in 1 year by Noah's flood because so much carbon dioxide and heat was generated that these just flourished like crazy in those months of the flood. And the conclusion was the White Cliffs of Dover confirm the biblical account of a global flood just about 4,000 years ago. The evidence is apparent when viewed through a biblical perspective. Take it or leave it, my friends. Woo. All right. Any questions about that? Now, this of course, is not quantitative. This is qualitative, because these are not, this isn't radioactive decay. But it's just evidence that 400 meters of coccoliths don't get produced in a year. For my colleagues and I, with all those radiometric dating tools, we feel that God's really given us some amazing ways to test and verify our understanding of Earth history. And we rejoice in the opportunity to study it in this way. Okay. One of the things that David Wu suggested was to give a brief overview of some of the things about our Grand Canyon book. The Grand Canyon, Monument to an Ancient Earth, is the title we gave it, but we added an important subtitle.
Mars.
Can Noah's flood explain the Grand Canyon? Now, as I was working on the title, a theologian whom I know strongly recommended that the subtitle should not be a question, because apparently at one point he put a subtitle as a question on one of his books and it didn't do very well. But as I began to think about our mission in writing this book, which is written expressly for the church, I realized I don't want to be telling my Christian brothers and sisters that have a young Earth view to take my answer and believe it. I wanted them to see how we do geology. We ask questions, we go gather data, and then we look for what the best inference is of understanding what God did to produce this collection of geological information where we find it. So we did, in fact, call it as a question to try to invite Christians to look seriously at the data. And there's a URL that you can, if you haven't ended up getting the book, that you could look at as a background for it. And if it gets away from you, just email me and I can send you the link. We selected particular authors because we wanted subdisciplines covered with somebody who has expertise as we put the book together. So 8 of the 11 of us as authors are Christians. There were a couple of topics that we just didn't have know a Christian colleague that was a specialist in that area. And these individuals who are not Christians certainly were sympathetic with our mission in writing the book, or of course they wouldn't have participated in such a friendly way as they did. One gentleman, in fact, was in a Baptist family, and they had sort of gone really strongly toward the young Earth side. So he's had great family, what shall I say, family angst over that issue. Several of the people actually have done a lot of work directly in the Colorado Plateau, which helped us to get a book that we feel has good, solid, modern geology understanding of the Grand Canyon. The lady who triggered it is Carol Hill, whom I'm standing by here. She herself lives in Albuquerque, New Mexico, and has an adjunct professor relationship with the University of Mexico and works with some of the permanent faculty and has done projects and research in the canyon itself. And about 7 or 8 years ago, she contacted several of us and saying we should write this book. And she took the lead at getting it started. And then she had the dubious task of sort of corralling all these crazy cats, if you will, who were writing pieces of the book and then putting it together. So we had sort of a long, challenging 5 to 6 years to get this published. But when it came out, we were just thrilled we got there. Now at the Grand Canyon, there is a canyon ministry, and they take vans like this and they drive along the rim of the canyon, and they tell the people that this canyon, the sediments were all formed by Noah's flood. The sedimentary rocks were all formed by Noah's flood. And then the canyon itself was formed as the water was receding away at the end of Noah's flood. The man in the picture here is Tim Hebel, and he was able to get his picture taken because I guess the people were away from the truck at that moment. And he is basically our photo editor of the book and co-author of 4 or 5 of the chapters. The flood geology community has been writing multiple books about the Grand Canyon, and these are the covers of 5 of them. In the book, which we treated primarily as a geology book, we didn't go into issues related to the interpretation of Genesis. We wanted it as a geology book because we wanted to be able to have it on sale in the Grand Canyon bookstore, which it is. So in the introduction, we just state the nature of the issues. We describe flood geology. We give a time frame for flood geology, and then we share a time frame of modern geology as those of us who are authors have done. Carol Hill, I said, was Albuquerque, New Mexico University. Steve Moser is department chairman of geology at Wheaton College. Tim Hebel is retired from the U.S. Geological Survey or a similar organization. So he has geology background. We were blessed with biblical scholars and theologians endorsing our book, including Jack Collins at Covenant Seminary, Paul Copan, Palm Beach Atlantic University, Wayne Grudem at Phoenix Seminary, and Kenneth Keithley, professor of theology at Southeastern Baptist Theological Seminary. So they were very gracious to write nice comments that we were able to put in the front of the book. Part 2, we address sedimentary rocks in terms of how sedimentary rocks form, the nature of structure of sedimentary rocks, and then using the present to understand the past in the rocks that we observe and study, and how did they form with the laws of physics and chemistry that God has built into the creation. In terms of geologic time, all geology has a relative time of seeing the passage because a big stack of rocks, inevitably, if sedimentary rocks, the oldest rocks are going to be on the bottom and the youngest rocks on top. So that's a relative age dating of a series of rocks. So as we look across from the south rim and we see the rocks, the oldest ones are on the bottom and the youngest ones are on top. So in the canyon itself, in the inner gorge, there are rocks that are igneous and metamorphic rocks and sedimentary rocks that were precursors to the direct deposition of most of those sedimentary rocks that we see. And this is a stack basically of 5,000 feet there at about the position from looking at the inner gorge up to the very rim of the plateau. This is a slide that I use in a lot of my geology for non-geology classes because I can explain to people who have no geology background at all that one of the things that we do in geology is we apply names to formations for communication purposes and for discussion. And this photo of the Grand Canyon is just a fabulous example to be able to show the Coconino sandstone, which is that very light colored right just below the rim. So that one has Coconino sandstone as an example. Another great one to follow that I like to look at is this red wall limestone, which shows up just like the wording says, red wall. And that red wall limestone forms one of the cliffs because it is a limestone and it's rigid and it maintains the structure. And this whole sequence are rocks that are Paleozoic in period, which I'll show here in a moment. And then everything down below this Tapete sandstone, which is considered at a great unconformity. Everything is pre-Paleozoic. That is back in the Precambrian. So these are the rocks then that are in the Grand Canyon. Okay. The inner gorge has rocks then that are to 1.2 to 1.5 billion years. So prior to the Cambrian. And even though I'm saying that the Grand Canyon has these, it in fact, however, is missing two of them. It's missing Ordovician and Silurian. So this is one of the very obvious reasons that the sediments in the Grand Canyon were not deposited in a continual sequence from one flood. So there's a schematic that we have in the book of all the Grand Canyon rocks. The flood geology community refers to this as the early flood stage. And then these are all Paleozoic rocks to us as practicing geologists. Up to the north, from Arizona into Utah, there's a series of rocks that are Mesozoic, and that's where all the dinosaurs are. So these little dots that we have beside that Mesozoic rocks, okay, are formations that have dinosaurs in. Even though they make the claim that the Grand Canyon was formed by Noah's flood, in the canyon itself, there are no dinosaur bones. There are no mammals. There are no spores of flowering plants. And the logical reason for us as geologists is it's because those had not yet been created by God in the methods that he used to do his creation. So to claim that that was formed by Noah's flood, but it has no dinosaurs, that's a pretty big hiccup for flood geology. I'll give one example that that Canyon Ministries that I mentioned with Tim Hebel takes Christians down through the river on a river float trip, and they tell the people that the Grand Canyon was formed by Noah's flood. And this particular outcrop is one that catches my attention because this outcrop is claimed by a flood geologist to be the result of soft sediment being deformed because it has no fractures. And this is what he tells people in the church as they ride along the river trip with him. In fact, when we examine it carefully, my colleague Brian Tapp is a structural geologist. I managed to keep my name off the cover as an editor, but I did work with Brian Tapp to write 2 chapters here in the middle. And he has the expertise that when he sees folded rocks of this type, he can identify the fact that they were hard when they were folded, and in particular because the different layers had a different ductility. You know, some were more easily squeezed and others were more rigid. There were differences. Those differences caused these red arrows through the fold to change orientation. If each of the layers had the same physical properties, this would not occur. And there is a close-up of it. And Brian Tapp, my colleague, was able to take a picture. And in the picture itself, he could see the folds and he can see the fractures. The rocks are fractured, fractured, fractured. But a PhD geologist tell Christians in the canyon, they're not fractured. It was soft sediment. That's a hiccup. Another comment that was said by someone that was standing on the rim in the movie is Genesis History. He said, looking between the layers, we cannot see erosion or significant channels to any degree, to any significant degree. And he made claims like that the mountains have arisen since the flood. Well, with plate tectonics basically moving from 1 to 3 to maybe 6 inches per year, mountains have not been built since 4,000 years ago. The claim that there's no evidence between layers, this is the red wall limestone down here. Okay, that's the red wall limestone. This is a 400-foot deep channel that has been cut into the red wall limestone by erosion at a surface. And it is then has a formation that has a mixture of land fossils and then marine fossils. When that surface was then flooded with seawater and refilled with sediment that had been eroded away from the red wall limestone. So those kind of comments going into a movie are just that is watched by Christians sort of adds to the confusion in the church and the division in the church. A chemist wrote this about the book. This is one of the best introductions to geology that I've ever seen. This section alone would make the book a worthwhile purchase, even if one does not have much interest in creationism. We were able to have a book signing at the Canyon, which was thrilling. And so they sell the book in the bookstore, and I think they still do, as far as I know. Here was a polite and gracious comment. This book beautifully, graciously, and thoroughly confirmed that the earth actually is very old. It offers grace and tact and kindness toward people trapped in the young earth idea marketed by flood geologists. I'm so very grateful to the authors for writing this book. Things like this that make it worthwhile, the endless hours I put into it and the others. Here's the example of ages that are somewhat discordant that I said I would talk about. Let's see, there's a section of the time frame. Here are the ages. This series of 4 different ages was done on a igneous intrusion into a shale down here, okay? So this is information that's been published in a flood geologist book. That was one of those covers that I showed you at the beginning of this book section. Well, when we plot them on the scale, samarium and neodymium are both essentially, neodymium and uranium lead are essentially giving us concordant ages because it's within the error bars of the measurements. Rubidium strontium was a little bit lower, but boy, not far off. And then potassium argon is less. And for us as geochemists, that would be the suggested possibility is that these rocks were heated up at some point during the processes that caused all these sedimentary layers to be tilted and uplifted. Because notice that down here to the lower left, the sedimentary layers are going like this. So there was some tectonics that happened at some point that lifted those rocks up, which meant there could be, rocks could be heated up when rocks are heated up, then some of the argon 40 can escape, so that this is an artificially younger age than original because of the argon being mobilized. Just a few comments then about Persian Gulf and Noah's flood that David asked me to chat about.
And one random question about Grand Canyon.
Yes, please.
Okay, so the Grand Canyon's like really wide at the top and narrow in the middle.
Yes.
So is that just erosion from wind on the top? Or was
No, this would be cutting back water, not primarily wind erosion. This would be just cutting back of the drainage basin. Rocks falling off the edge and then the Colorado River carrying it down.
It's not like the river was wider in the beginning and then
no.
Okay, so just erosion.
That's erosion. Just over about, it's estimated that the canyon was cut over a time window of about 6 million years.
Okay.
I'm going the wrong way. Excuse me. Okay. Here's the context of the Persian Gulf at the present time. And so you would identify that basically this is Kuwait and then Iraq up here, etc. However, you remember from last talk 2 months ago, I showed you that there was evidence that we have an awareness that there was a 2-mile thick ice sheet across Canada and Scandinavia, which means lots and lots of seawater had been evaporated from the sea and was stuck up there on land. That took sea level down much lower. It took sea level down approximately 400 feet lower than it is today. And so right in here at this entrance to the Gulf of Aden and the Persian, 15,000 years ago, the Tigris-Euphrates River Valley was flowing on down as a river and then out over that sill. As sea level rose with time, then it flooded back into this area and caused it to be the Persian Gulf that we know today. Now the sea level, the 15,000 and the 6,000, that last figure you see is 15,000 years ago. Here's the graph of sea level rise from here, right about in here is 15,000, okay? The vertical scale here is in meters, so this is 100 meters, 120 meters lower than sea level is today. And then I actually had a chance to do one of my first oceanographic trips down here to Barbados. Now, I wasn't collecting samples at that point for this sea level work, but I'm aware of it because my laboratory was somewhat involved with that. And then between 15,000 and about 6,000 years ago, as the ice melted from the ice sheets, went back into the oceans, then sea level has risen that 400 feet. And in the process, then that's flooded, formed the Persian Gulf. And in addition, this extra area that's even further inland than we see today. Ancient cities were always built near a coastline. So there's Ur of the Chaldees. And over the 6,000 years, river sedimentation has built the delta further down here in all of the area that we know now as Kuwait. There is some evidence that I'm told that when this river was flowing prior to 15,000 years ago, there's some evidence that's now buried, underwater in the Persian Gulf of some habitation along this river area. How strong that is, I'm not sure. I haven't done a lot of digging into that question, but that would be consistent with, if mankind was living, that they would live along the river. Okay. Now I'm thinking about the flood. as I've been giving these talks, we had Hurricane Harvey hit Houston, okay? In Houston for those 5 days, over those 5 days, like something pushing toward 2 to 3 feet of water fell on Houston. And I think then of the Tigris-Euphrates River Valley. If God had storm clouds fall over this portion of the Tigris-Euphrates River Valley to pour rain down that would make a couple of feet in 5 days, we're told that the flooding period was 40 days. It's not hard to envision that this whole lower Tigris-Euphrates River Valley was just bloody flooded, and flooded for, who knows, 15, 20 feet of water. The gradient down the Tigris-Euphrates is very low. This is flat land. If from Ur the Chaldees in here, it's like 50 to 60 miles over to these mountains. And it's quite some distance, also miles to the west. So Noah could be looking out and everything is covered with water in that. I don't know. This is, of course, this is speculation, but the terrain there is indicative that catastrophic flooding in terms of the quantities of water would put that area underwater for a long time. And of course, the Bible describes it, in a year-long perspective. But who knows? That's a tough question. So these were the things that I said I would talk about. Please ask questions.
If you go back to that last picture, is Israel kind of the white area up above the triangular, right up there? Got to visit.
Okay, here's the, let's see, there's the Dead Sea. There'd be the Sea of Galilee.
Okay. Ephesus is where then?
So this
Ephesus is like 3 miles inland now. And when
Ephesus is over in Greece, isn't it?
No,
Yeah.
Turkey.
Huh?
Turkey, yeah.
Ephesus is up in here somewhere.
Okay.
Or even west of that.
Yeah, maybe. All right.
Now,
That's a
Joppa, Tyre and Sidon, they're along in here somewhere.
okay. I'm trying to relate.
Go ahead.
Water level coming up. Did you say 300 feet?
Well,
In time? The Persian
yes,
Gulf?
but I'm trying to think. Mediterranean. The Mediterranean did not go dry in this time period. So yes, coastal areas along there would be down also. I do not know what the sill level is out at Gibraltar. I do not remember. But of course, all of this drainage is to the Persian Gulf.
Yes.
could you go back to the slide prior to modern times of the Persian Gulf? Yeah. So if there was a big rain that was deposited, couldn't there be something that would block the flow of the Euphrates down where that oval is, and that would have backed up during the flood? Does that make sense?
Well, it's okay.
Restricted there. I mean, if you had
Okay,
trees
when sea level is low between 15,000 and then this would start flooding as sea level was coming up and up and up. I don't think, I'm not sure we can know quite where in this sea level rising. Well, let's see, if the sill is at about 300 feet, I guess there could be a sense of when the water from the ocean began to come in and fill and flood that area that's now all Persian Gulf. I haven't looked into that in terms of the timing of when. I just sort of took the endpoints and saying sea level is low 15,000 years ago, and it's about like it is today 6,000 years ago.
And where are we placing the flood?
Okay, a question is, did the water, it seems to me as though the water coming into the Persian Gulf itself certainly forced people to leave where they were living along that river and go to higher ground.
So you're saying that the time of Noah's flood, the Persian Gulf would have been there?
I don't know.
Okay.
I don't know. It's a question of how well do theologians or Bible scholars try to put an age on Noah. If they can do that, some Bible scholars think that there's that the genealogies are father to son or father to grandson. Others tend to say that it only affirms that the next in the sequence is in fact a descendant of the purpose was a continuous blood link, but it doesn't necessarily have father, son, or father, grandson. So could it be 7,000 years ago? Could it be 15,000 years ago? I don't know.
I have a question about the Chaldees. Earlier, you showed a slide where is right next to the water.
Yeah.
Another one is it wasn't next to the water. There it is next to the water. And later, like what happened here again?
This would be during that time period from 6,000 years ago to now. This sediment was deposited as a delta.
Oh, okay. I understand now. Thank you.
There, it's up there. Oh, going the wrong way. Got to do this. So there, it's pretty close to the water. 6,000 years ago. There it is today, with with 6,000 years of sediment being carried by the Tigris-Euphrates river valleys down to the Persian Gulf.
Of course, nobody really knows when when Noah's flood happened. Hugh Ross has come out arguing that the flood was about 40,000 years ago, and so that would be when the Gulf was dry, as you were showing.
Yeah.
And
if it was 40,000 years ago, then that's the way it looked.
Right, and he posits that that it came in and it was even bigger than you said, but still just confined to this one area.
Yeah. It's a tough question. We don't have answers, but this is the area. Noah lived in here somewhere, and the flood is described. I sometimes, I have a conviction that however it plays out, God achieved the things, his objective that he intended to achieve in the killing of wicked mankind. Now, what and how and when, unknown questions.
Ken, can you go back to pictures showing the Grand Canyon, please?
Yep. Kind of what section? Let me get the big sequence.
Any section showing the extent of all the different layers.
Yeah, there.
That's a good.
Oh, there you go.
Yeah.
Where'd all that material come from? Glaciers push it down, or why over millions of years do we have all these different? This is geology, not even 101. We're back to geology 0.
Yeah.
Where did it all come from?
Okay. Sedimentary rocks are formed in lakes and formed from rivers and formed in the sea. This red wall limestone.
So this is showing that was all the,
So this
the
all
continent
was at sea level during the deposition. Coconino sandstone, and there's another limestone on top of the Coconino sandstone.
But
So,
if you were to do a cross section pretty much anywhere in the world, you're going to see layers.
that's right.
So
And geologically, on the coastline, the nature of plate tectonic movements include that the seas come into a coastline and they recede from a coastline. And so there's lots of continual deposition of sediments on a big pile. Then in the case of the Colorado Plateau, this whole thing was lifted up. Basically, this is up now about 8,000 feet. The South Rim is 7,000, 8,000 feet. So those are plate tectonic things that are happening from deep in the crust.
So
But difference, for instance, very, very different from the Appalachian Mountains where I grew up, in that even though we have in the Appalachian Mountains, the Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, these same rocks, in the eastern part of the United States, they're not in a flat plateau like this. In the Appalachians, they're all folded up. Okay, lots of hills up and down. So the tectonic activity during the time of the construction of the Appalachian Mountains is completely different process than this case that uplifted similar aged rocks in the western portion of the United States, or in the central portion in Colorado Plateau, had very different responses.
So part of this understanding, as far as where this stuff came from, would have to go back to times probably close to Pangaea and the breakup of Pangaea into its separate components.
That's a lot of it. But Pangaea, the North American continent, was already formed in Pangaea. Okay. The Pangaea diagram that I showed you starts at 180 million years ago. And 180 million years is, where's one of my cards real quick?
It's up in the Mesozoic, right?
Yeah, yeah. Let's see, Pangaea breakup is Jurassic. This is just Mesozoic. Let's just put it in the middle, Triassic. Pangaea breakup would be somewhere in here.
So they talk about inland seas making up most of what is now the plateau regions of the United States, the Colorado.
Where there's a particular plateau, or let's see, an inland sea. Let's see, yeah, up and down the eastern side of the Rocky Mountains, the whole way up into Canada, the Cretaceous was an inland sea. That would be, Cretaceous would be, yeah, late stage Mesozoic would be up in here.
Okay.
Yeah.
So this is previous to that. Okay.
Yeah, this is all previous to the Cretaceous. Yeah.
So Ken, would it be fair to say the whole rock of Grand Canyon has been formed by layers and layers lifted up from the plate tectonic, crush up the mountain, lift up the mountain, and then
the whole thing is a big plateau was lifted up by things happening down deep in the crust.
And then through the years, through the glaciers, waters flow, it begin to carve out all this shape so that it has this center gorge area, and then a lot of it has been carved out by glacier and water. Is that correct?
Mixture of glaciers and water, lots of, yeah, water over a long period of time.
Thank you.
Yep.
Well, guys,
You folks ask such good questions.
thank you. No, we are such a good lecturers. We're gonna go all rushed out to buy this book now, Monument of the Grand Canyon. I have a copy, but you can easily get it at Amazon.
If any of you, if any of you are the type that want to have an autograph copy, just let me know and I'd be glad to sign one and send it to you if you want.
Okay, great. Anyway, do you have any more burning questions, guys?
Would you have an interest in my sending you that little copy of that Chalk Cliffs of Dover with those numbers?
We would love it. Yeah, send it to me and I will distribute it out.
Yeah.
Okay. And Ken,
What about, I think several of you have had really keen interest in sort of understanding the radiometric dating. I'm going to send also to David 2 papers. In fact, the one paper will have that table that I showed you from the asteroid impact. It has those 147 or 80, whatever it was, analyses. The one paper will have that. I'll send you 2. One is written by Roger Weens, who's a Christian. So his paper is a Christian's perspective on radiometric dating. And he writes it so well that it has been on the American Scientific Affiliation website for like 20 years. And it is the largest number. It's the article that has had more downloads than anything else in their whole collection. I'll send it. So that's one. The other one I'll send you is by Brent Dalrymple. He's not in the Christian community, but he was the geochemist that helped to establish the potassium argon dating method, working on that data that I showed you with respect to the Pacific Ocean Basin and the Emperor Seamounts and the Hawaiian Islands. He worked for the U.S. Geological Survey for a long time and helped to develop that methodology. And the title of his, it will be Radiometric Dating Does Work. And yes, it does work. And he gives multiple examples. So I will send those 2 papers to David, and then my little piece on the Chalk Cliffs of Dover.
Oh, thank you, Ken. Ken, you are such a good speaker. I'm going to have to find some other topic that you had to get you back. Okay.
Well, maybe sometime the Lord will give me a chance to develop something a little more robust on.
And if you can, come to San Diego for vacation.
But I don't know.
Yeah, if you want to come to San Diego, we'll be very happy to host you.
Oh, thank you.
Yeah. Okay. We run out of time. So Ray, can you close up in prayer for us?
Sure. Lord Father in heaven, thank you for everything. And thank you for giving us curiosity about all the wonders that you have created. And thank you for the blessing of people like Ken that help elucidate the difficult areas that most of the rest of us don't understand and want to. And thank you very much for David and the rest of the San Diego team that put together meetings like this that help us learn more and more about the wonders of creation. Thank you once again. In Jesus' name we pray. Amen.
Amen.
Amen. Thank you, everyone. And see you next time. We'll have a little break in August and in August, and then we'll come back in September for Cynthia Chang. She is a NASA astrophysicist. And there'll be a I think she's going to talk about the moon with a lot of nice picture.
Great.
So
Good
thank you
night.
guys.
And I don't mind inviting you that, if you have questions, just get my email from David and send a question, Some of those came up, I could do some digging and learn some things too.
Yes, we would do that.
Thank you.
Thank
Thank you,
you.
Thank
Ken.
you very
Great
much.
presentation.
Thank you, Ken.
Very much.
You're very welcome. Delight to be here. Glad to join you.